So let's see, we're going to have one last burst. Lecture 15, large molecules. So in spectroscopy, usually large molecules are trouble. But actually, there's some times when they can be an advantage, and you'll see. So last lecture, large molecule PLIF. This is the things we're going to cover, end up with the future. I realize now that this is temperature. This was temperature image over a soldering iron. So this is like a hot soldering iron, flows coming over there. And these were temperature contours. I don't know, they're separated by maybe, I don't know, 20 degrees or something. But I believe it actually wasn't, it was a single shot PLIF image, but I think it was probably acetone or pentanone and not toluene, so I'll fix that. So I want to take you now to flow tracers. The idea of a flow tracer is that you can add something intentionally rather than watch it being formed in combustion. You can add it intentionally to some advantage. And acetone is the thing that's the easiest to understand and we've done the most with. Then we'll talk about 3-pentanone, which is just a little bit bigger. These ones are ketones and they're just different sizes. And this has progressed to the point now that some of my students have done this in IC engines. We also work sometimes with CW PLIF rather than pulsed. And we've been working with toluene lately. It has some advantages for measuring temperature very accurately. So that's what we're going to talk about. So I mentioned last time, PLIF began about 30 years ago. My student's name was George Kitchikoff. He has a company in Washington. I had a technician who then got so interested in this, he became a professor at Harvard, which is quite an evolution. And then Jim McDaniel's a professor at University of Virginia. And, but we're going to go from that and we're going to talk about the present, which is trying to use ketones to control the fluorescence quantum yield, shown here as V. So the fluorescence equation is that the fluorescent signal is the photons in. So I take the energy in megajoule or in millijoules, divide by h nu, and this is kind of photons in. The number density and the cross section of the absorption. So now for cross section of absorption, I'm going to use sigma. So in sigma is the photons absorbed. Phi is the photons emitted, or quantum yield, and then eta is the fractional collection. So photons collected is always kind of photons in, fraction collected, fraction re-emitted, fraction collected. Think of it that way. So, and we could do this in a plane or we can do it at a point, doesn't make any difference. This looks like we've got, and usually we go from one electronic state to another, and then some light comes out of this upper well and we capture it. The return rate, Q electronic, would be the dominant term usually. But we're going to get around this now. So I told you a little bit about biacetyl, which Pilling calls diacetyl, and acetone. And the idea is that we would try to add a tracer which had simple interpretation for Q. That's really the idea. Simple interpretation for Q. So we did this in the 1980s with biacetyl. So it's really two methyls and then a CO in the middle. I didn't say that right. It's methyls and a CO, and then it kind of can split right here. So it looks something like this. It's smelly, it's hard to deal with, it had a low vapor pressure, it had some problems. It also is very highly quenched by oxygen, so we had to use it in systems that had no oxygen. But then my student from Spain, Lozano, came to the rescue and said, we can't do this anymore, but acetone shows high potential. Notice that this is kind of similar in structure to this one, only now we have only one of these carbon double bonds. That's called usually a carbonyl. So those things have some interesting fluorescence properties. They're all ketones. So the things where you have this double bond are called ketones. So we could be acetone, pentanone, and so on. When you excite one of these big molecules, and if you look at the absorption spectrum, it's kind of a continuum. It's not discrete lines. So the advantage now of this big molecule is that all the lines overlap to the point that it's just a continuum. They tend to be centered at around 250 or 260 nanometers. And when you excite them, say here, and the fluorescence comes back, and you perform an absorption, a fluorescent spectrum, it looks like this. It's usually at longer, different wavelengths. Therefore, if you illuminate it here and put a filter, a bandpass filter here, you collect only this, you don't see any laser light. That's attractive. So usually fluorescence is shifted to longer wavelengths. Now the advantage is that I'm going to show you is that we can arrange for Q to be a constant. Then that means that the signal is going to be proportional to the number density of the absorbers. And it's going to be simple to interpret, with the exception of the fact that you have to worry about oxygen quenching sometimes. So it's going to give it, and it's going to give us strong signals. It's going to give us strong signals. It's going to be accessible in the sense that this region here is compatible with several pulse laser sources at 248 nanometers for krypton fluoride, 266 for quadruple jag, and so on. So you can find fairly straightforward lasers to use right here. The application might be to fluid mechanics, heat transfer, fuel air mixing. Problem is that it's a hydrocarbon, so it burns. So if you heat it higher than, say, 1,000 degrees, 1,100 degrees, it burns just like the hydrocarbon fuel that you're going to burn. So it doesn't stay around like NO would. But it has some advantages. So if you're interested in lower temperatures, if you're interested in fluid mechanics, maybe you don't care about high temperatures. So now what's happening? We have a group of states. This is the low electronic state of this molecule of acetone. It's called an S0. The S means it's a singlet, which means that 2s plus 1 is 1, or the spin is 0. That's the lowest energy electronic state of acetone down here. All these levels are just to represent the fact that there's a lot of energy levels all smushed together. The next excited electronic state that's a singlet is called S1. So S0, S1, so whereas I said capital X, capital A, now for these molecules we go S0, S1. But some molecules can also be triplets over here, so they're called T's, T3 say. They have also some energy levels. So when you're here, you can go into here, or you might possibly go over here. But the molecules don't like spin change. So you don't really absorb light and go over to here very easily. So we send in a photon which has some length of arrow, and we go from some grouping of states here to some grouping of states up there. And what happens? When you're up here in some states, you're going to see we can have energy transfer, we can have re-emission, and you can also have something where you go between this system, and that's called inter-system crossing. It has a certain transfer rate Q. And that's going to be a big number, but it's going to be more or less constant if the temperature and the pressure of the flow are within reasonable ranges. Now, the utility of acetone is that it's safe. It has a high vapor pressure, so it's easy to produce enough vapor. So it's cheap, non-toxic, easy to handle. The fluorescence lifetime is about 2 nanoseconds. And it doesn't really care too much if there's some oxygen around. So if you excite it and watch it decay, it goes away in 2 nanoseconds. The quantum yield, that is what fraction of the absorbed photons come back out, is approximately 0.2%, 1 in 500. So if you absorb 500 photons, 1 comes back out. The good news is that fraction is pretty much fixed at room temperature. So now if we look at our fluorescence yield equation, which is A over A plus Q, and if you recognize that this Q is actually even still bigger than A over Q is small, that's the 0.2%, then the signal is essentially a constant times the number density of the absorbers. All of a sudden we're getting around the quenching problem without killing the signal entirely. So instead of having fluorescence quantum yield of 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, it's not too bad. 2 times 10 to the minus 3. Because you can put in a lot of acetone. It's not 10 ppm. I mean, you can put in more. So this is a really good thing, and people now have used it around the world. Lozana was the student, Brandon Yip was a postdoc from Yale. Now we had to study this a little bit, and here's the absorption spectrum, which peaks at around 270 nanometers. So that's a convenient place, except you have to worry sometimes if you're doing it in a system where there's some other hydrocarbons, they might also absorb. So this is going to work best if this is acetone in air or acetone in something that does not absorb in the UV. There's the fluorescence spectrum. And, oh, there's corrected. So when you measure the fluorescence spectrum with your spectrograph, you have to kind of be careful that you've corrected the spectrograph for some non-ideal effects. So there's the corrected version and the non-corrected. But the main thing is that it peaks at around 480. So it shifts to the right, so you'll be able to discriminate all of this light from this light, the scattered light from the laser. So, and we won't worry about this little problem right here. So I'm going to give you some examples to kind of illustrate how well this works and how a student who only wanted to study fluid mechanics was able to use this. His name was Scott Smith. So he wanted to study fluid mechanics. We came up with this scheme. He wanted to study mixing of a room temperature jet in a crossflow. The crossflow velocity was 5 meters per second. The jet diameter was 5 millimeters. The velocity ratio of the jet, so this jet was moving about 20 to 1, so it would have been 100 times faster than across 100 meters per second. So the question is, how does a jet of this diameter mix? And this is a single shot image in the central plane of the jet of what is therefore going to be the mixture fraction. So it's isothermal, it's isobaric, it's slow speed, essentially incompressible, tailor-made for this rig. This laser had no knobs. This camera had no knobs. He just turned them on, formed it into a sheet, took pictures. Because this is an unintensified camera, it has huge dynamic range. It was unintensified. So this picture, where this is the intensity distribution, we had a very wide dynamic range. You can see, so this would be a mole whatever, this is the pure jet fluid, which was comprised of, well, it was at atmospheric pressure, so 760 torr. The most we could have had is around maybe 20% of acetone in the, was probably air, or might have been nitrogen. So you can see these really weak trailing structures that I don't think people had seen before because their signals are so small compared to here. And then you can take a cut along this line and you'll see this intensity distribution. Or you can take a cut along this line and you can see this intensity distribution. And neither one looks like a textbook. So isothermal, isobaric, PLIF made easy. I don't remember at that time we did this. That laser might have been a $50,000 laser, might have been a $30,000 camera. It was certainly well less than $100,000, probably less now. But look at some more pictures. So then this works so well. So he studied this as a function of the cross-flow ratio of the velocities, momentum ratios. He wanted to study this. This one's really interesting. Look, if you take a horizontal, this is a vertical plane. If you take a horizontal plane and take a cut through there, that means you have to take another image now, the plan view. Look at this structure. If you take an end view, you see this funny little structure down here. And if you take these at different times, you see it like flipping sine. It's really quite interesting. So what that shows you is that that student set that experiment up in days. So it was a pretty simple experiment. You could just study fluid mechanics. It was because it was isobaric, isothermal, Q is a constant. The signal is directly proportional. Now you take a picture of the flow field with a uniform mole fraction. And then you store that correction image. You also take an image with the laser off. So you have to take a background correction. You have to correct for the sheet distribution of the laser, and then you're done. Instantly you're to mole fraction. So these are really images of mole fraction, which is mixing. So how did we do this? Or how did he do this? Remember, here's our signal strength. It's the number of photons in, the path length. Remember, when we do fluorescence, you get back to path length. That'd be the size of the region that the pixel is looking at. Number density of absorbers, cross-section, fluorescence quantum yield is absorption fraction collected. Now, behind this is a lot of physics. I'm going to tell you about the physics because we want to use this in situ. So what happened? This is very interesting. My student discovered acetone. People in Europe discovered acetone a little later. We went to a meeting where people all said, here's acetone, it's great. And one professor was saying, and look how the signal doesn't change with temperature. The other professor said, no, my signal does change with temperature. And it turned out it was because they were using different wavelengths of illumination, and that we hadn't yet realized that you have to think about temperature not because of the quenching directly, but because of the number density. So anyway, over time, everybody uses acetone, and it's very simple if it's isothermal and isobaric, but if I wanted to do this in a compressible flow field. If the temperature is varying and the pressure is varying, you have to think a little bit more. So so we built a model. The student's name was Thurber. People now use the Thurber model around the world. And it's an energy transfer model. So we imagine this ground electronic state with a whole bunch of energy levels. And we send in a photon with this length. And for simplicity, we say, imagine the molecules with the average energy. So imagine the average thermal energy. That would mean you'd be parked right here. So you have 0 electronic energy. You've got this average thermal energy. On average, here you are. That means that on average, you're going up here. And what happens when you're up here? You can undergo what's called system crossing, intersystem crossing over to the triplet manifold. Or you can undergo vibrational relaxation. And if you went to Pilling's lectures, you would have heard him talk about delta E down, where there's an average amount of energy transferred per collision. Or you can fluoresce. So you start here, and then you have a snapshot of time. You can do this, or you can do this. If you do this, that's your signal. If you do this, you're done. You're gone. If you do this, you get another chance. So you have to sum the quantum yield over successive steps of time, as long as it's still here. And that actually was the essence of the model I had at the very end of my notes for lecture 13. So you have to have this model, and it depends upon some characteristic rates. And we had to build this, and we're still building it actually for different species. So there's parameters in here, they aren't really known. We had to build a model. And why did we build it? Because we need to understand how to do this in a compressible flow. That's a lot of work. So then we finished that for acetone. We went on to 3-pentanone. And here's why it got really interesting. This is the relative fluorescence signal as a function of temperature if you excite a different color. So you do your experiment at 248, you pump in 248, you watch the photons come out. And you compare the photons that come out with temperature, and you see how it changes with temperature. This was the problem that we had at the European meeting at some nice place in the Lake District in the United Kingdom. This is why this professor is saying, I don't see any change in my signal, and this professor is saying, I see a huge change in my signal, and because they were using different wavelengths. So this got me really interested. And so what you can say is, if you want to measure temperature, boy, this is a good place to be. This signal changes like 3 orders of magnitude over a few hundred degrees. So the relative fluorescence yield is strongly temperature sensitive and wavelength sensitive. So if you don't want it to change, you use 308. So we're starting to come to grips with compressible flow fields where there's variable. So now you want to measure temperature. The thing to do, we always take ratios. So now you take you take these signals and you take certain ratios. So what if I excite at two colors, 308 and 248, bang, bang, take the fluorescence, take the ratio, I can get that it's this temperature sensitive, extremely temperature sensitive. So basically you're illuminating the same molecules. Only thing that's changed is sigma and phi. Only thing that changed, everything's the same. This is the same from pulse to pulse. This is the only thing that changes. So if you understand, the photophysics is right here. We always work on photophysics. If you do that, you can measure temperature really accurately. And that was the basis of that picture that I showed on slide 1 of the soldering iron. So he also said, well, sometimes people want to study mixing. So I think this was a later student. This was a heated jet. Instantaneous temperature and mole fraction images from a heated 3-pentanone air jet using this wavelength pair. So you go 2 successive images and you take the ratio, and from the ratio you get the temperature, and from the absolute value of either one, knowing temperature, you can get the mole fraction. So which is which? This is the 3-pentanone air ratio, and this one must be temperature. So you do something like this. You have a pulse of laser light, goes through your experiment, another pulse of laser light, one camera, bang, bang. It's called the, I forget the name of that camera, but you could take 2 pictures in two microseconds. So by understanding the photophysics and having measured the fluorescence quantum yield and the absorption cross-section, you can do quantitative thermometry quite well in a flow field that's not isothermal. So if it's isothermal isobaric, this is about as easy as it gets. If it's not isothermal isobaric, you have to pay attention to the photophysics. So then I had a couple of students who were interested in engines, and they took these ideas to Sandia and they did them. So this was in the homogeneous charge compression ignition engine group at Sandia. People around the world have developed techniques for imaging inside an engine. And you typically have, you might illuminate, you have an optically accessible engine on this, and you send in a horizontal sheet of light. The fluorescence comes out and it goes out, this piston goes up and down, but it bounces off this mirror and goes to your detector. So people have learned how to take images inside engines. And in homogeneous charge compression ignition, they're really interested in what is the temperature and how uniform is it as they do the compression. Because the idea is that you want to control the ignition in that engine, more like a diesel. So they used another wavelength, these 277-308, which you can get by a Raman shifter. So we did some photophysics to decide what colors to use. They used 3-pentanone as a tracer. They were interested in a variety of questions. They want to know the temperature. They want to know the EGR recirculation. And here's these pictures that I can't remember now whether this was David Rothamer or Jordan Snyder, one of the two. But here's the temperature that they got. And you have to, you see different colors, and you get close. All these temperatures are only different by maximum of 100 degrees. So this stuff's really, or is it 200 degrees? 200 degrees. At different engine positions. And they were really interested in trying to understand the mixing, the mole fraction of the air. This is like an EGR question, and they were able to do that too. So those are pretty good. I think that's probably as good as anybody has ever done in the whole world with that idea. So you could see that it's pretty much mixed out at the bottom of this stroke here. Then, they came up with a scheme where they could just use one color at 277, And they were going to monitor the compression. Okay, this is a case where the mole fraction is fixed. My strategy, you fix the mole fraction, measure T. When they're both varying, you got to use two colors usually. So these are now different crank angles, and what you can begin to see is that the temperature starts to get a little bit non-uniform. Why do you care? Because it's going to ignite where it's hottest. There's the hot spot right there. So the fluid mechanics of mixing in the engine keep it from being a completely uniform, homogeneous charge compression ignition engine. The sensitivity was they could detect about 5 degrees, which is the best I'm sure that's ever been done. So I'm not an engine person, but I guess what I'm trying to do is show you that PLIF, made simple, even in a difficult experimental setup, is pretty powerful.
Professor?
Yes?
What temperatures do you need to get to, or what limits the temperatures you can use with 3 pentanone? When
Okay,
does it start going?
so there's two problems. Assuming, okay, the first problem, what temperature can you use in use-3 pentanone? If you look back on my plot, the signals are strongest at low temperature. It works best at low temperatures. The signal strength goes down with temperature. That's one problem. So you can't really get enough signal once you get colder than, say, 800 Kelvin with 3 pentanone. Other problem is if you get it hotter than 1,000 degrees in the presence of oxygen, it burns like the fuel. So it's gone. So it's more or less limited to, say, under 1,000 degrees, maybe under 800 degrees, and it works best at low temperature. So this would be fantastic if you wanted to study mixing at, 270 Kelvin. And phenomenal signals. Now, there's a lot of interest in trying to look at high-speed processes, mixing at high speed. So in the engine experiments, they get 1 shot per experiment. Take an image. They have to wait at least 1/10 of a second before they take another one. So they have to kind of decide where they're going to take their image. So you build up your information by taking single-shot images in a given, in certain cycles. And sometimes they skip fire. But anyway, how could you go about getting high-speed imaging? Well, the people who had a lot of money bought high repetition rate lasers and then high repetition rate cameras. So for a while we explored what could we do with a CW laser and a high-speed camera. So we tried an experiment where we had a CW laser with 5 watts. That's not a particularly high number. It's by higher. And we frequency doubled it. We formed it into a sheet. By that time, we had about 250 milliwatts of light going through a jet and onto a power meter. So this is a jet with okay, now we're switching to toluene. Toluene is an aromatic, and it gives stronger signals. That's why we did it, stronger signals. It has a problem in that it's sensitive to oxygen, so we have to do this in nitrogen. But you get big signals. So you have a wimpy laser, but you've got a gas with strong sigma phi, photophysics. And the question is, how fast could we do this? How could we get movies of a jet? So we had to study the photophysics and what size should you make the beam and how small a region should you image and how does it vary with the laser power in milliwatts from around 250 down. And let's see, so we had 2 different results here. Here's one when we had we're looking at regions 50 microns by 50 microns by 400 microns. So we're looking at really small regions. That's the black one. And so that's the signal, this is the detection limit in percent. If you go to 400 microns by 400 microns by 400 microns, you get detection limits that when you have our maximum laser power, our detection limits are like 0.5% of toluene. So already you're beginning to see. That means we could probably look at mixing and measure changes of about 0.5%. And here was our first attempt. Now we didn't have a high-speed camera. We had to trick it. So we took some images. The flow is downward. We took some images, which is essentially toluene mole fraction here. And we could also take some single shots. And then we could take the difference between the single shot and the mean to look at the difference. And that presumably is kind of what we would see if we could do this at high speed. So when you look at that, you'll see you could really see the structure of this jet mixing, even with this CW laser and a artificial fast camera. So I think this has got some potential also for high-speed imaging, because we could do this at any speed. As long as you get enough photons, you could go as fast as you want. Whereas some of these high repetition rate lasers you buy are kind of limited in what they can do in terms of frequency. Okay, back to this. I want to show you now how you can image temperature sensitively with toluene using one camera. So we're kind of back to something like this. And I'm going to do this. I had a student who finished. We did this in a shock tube. And so he built an extension on our shock tube that was square. And he put windows on essentially on the two sides, on three sides, and the end. So basically we converted our round shock tube into a square one, and we put windows on. So that we can look inside from different directions. And I set him the question of, could we measure the temperature in the boundary layer in the sidewall behind a shock wave? Could we possibly measure, and how close to the wall could we go? How close to the wall could we image temperature? That was his goal. And we use different configurations, but usually use a pulsed UV laser, forms into a sheet, and that sheet might go through horizontal, or it might come through in the end, but we'll come through and then we'll look, you always look at right angles. And we would seed our test gas, which was nitrogen, with toluene. So in the case where the end wall is here and the side wall, and the incident shock, the side wall is here. So the incident shock is moving this way. It's going to bounce off this end wall and come back. So the incident shock wave looks like a line here. So this is the pre-shock gas, and this is the incident shock's going this way. So this is the gas that's been shocked. This is the gas that's not yet shocked. It's colder, so the signal will be higher. And so we did this at initial pressure 44 torr. Post-shock pressure was 204.24 atmospheres. We had 7% of toluene. Shock speed was 600 meters a second. And now this is what we see. So here's the end wall. The shock, and we're not looking across the full width of the shock tube. So here's the shock tube, and the shock wave comes down this way, bounces off, and goes back. So this is the reflected shock wave in what's known as the bifurcation region, which nobody has ever observed except by line of sight Schlieren or interferometry. So we're beginning to see the power of PLIF to look at 3D structures. Now, what's the signal sensitive to? Density and temperature. So we have to be careful what the signal is. The signal, it depends on density and temperature, and so in different regions there's slightly different pressures, so you have to be careful how you interpret this. When you go back a little bit longer in time, this must be 150 microseconds. The region is growing. You can see, if you're a shock tube person, you'll recognize the structure. There's kind of a turbulent jetting separation. So that's pretty amazing. It's the ability to see these things. This was at, now it's at 200 microseconds, so the shock wave is out of the field of view. And you see some very irregular structures that are left down here. And here's this thing right here. Here it is down here. So you can see the power of PLAF to look at flow field structures in a transient flow field. You just have to be careful what are you imaging. You're imaging toluene in a way that depends upon multiple parameters. So you might have to compare this with a calculation. This is a comparison, I think, with a code. I think they call this the Charles code. Oh, here's the simulation. They use a code called Charles. So here's our experiment. Here's the simulation. This is the end wall. The shock wave's going to the left. Notice how the shock wave is not perpendicular to the walls. Pick that up. Here's the separation bubble. We pick that up. Here's the sidewall boundary layer. We pick that up. But when we go to this condition, theirs looks smaller. So there's some details that are still not right in their simulation. If you blow this up and look down here, there's a very interesting. Look at this. It's just like a textbook, except for this jetting structure, which is turbulent. And let's see. So this is this is like a blow-up of a very narrow region as a function of time. I don't remember what I did that for. Okay, so that student also left, but we showed, and I guess I left it out, it's too bad. I should have shown you the profile where he measured temperature next to the sidewall. Bottom line, he was able to measure temperature within 25 microns of the sidewall. So you could blow it up and you look at a little teeny region that's like maybe a couple millimeters wide and a couple millimeters long, and blow it up. And if you learn how to deal with the reflection from surfaces, he got within maybe 25, 30, 40 microns of the surface. So remember, there's no particles, this is just a tracer. So understanding the photophysics let him measure temperature close to the wall. And he showed good agreement between his boundary layer calculations and his measurements. I've had a student trying to learn how to measure temperature another way using two cameras. He's interested in hypersonics, so we look at this separated high-speed flow over a wedge. And so, and his idea is that he'll use two cameras. So here's the fluorescence spectrum, and it's shown here at different temperatures. Okay, I'll blow it up. So here's the there's the fluorescence quantum yield as a function of temperature. So the point is there's hardly any shift on the short wavelength side, but there's a big shift over here. And that suggests that what you want to do is you want to use two filters. So there's a single laser, but there's two cameras. One camera looks at this wavelength region, one of them looks over here. And then that signal is going to be strongly temperature dependent. And he looked at different filter combinations and gets these plots. This is a plot of the ratio as a version of temperature for different combinations. So the idea is one laser pulse, two cameras. Each one looks at a different spectral region. You take the ratio, and that would be single laser, two camera thermometry. And he did this in this problem here, which is the supersonic flow over this wedge, Mach 2.3. And he compared what he measured with what he calculated. A little bit noisy still. Then he went to this cylinder flow. Now it's more interesting because you get variable density and temperature going on. Looks pretty good. And good agreement with his computations. This would be along this line right here or along this line right here. Looks pretty good. And then the jet and cross flow. It's our generic scramjet problem. So we have some jet coming in probably about here, and he's just measuring the temperature. So he's got a toluene, he's got toluene in the flow field, and he's going to take ratios to get temperature. So this, in this case, he doesn't care about the mixing. The ratio gives you T. And you get some pretty good pictures. Okay, let's see here. That student's still there, here. Okay, so what do I think about the future of PLIF? I think it's got high potential for looking at some flow fields, especially shockwave boundary layer interactions, IC engines, scramjets, fluid dynamics, plasma enhanced combustion. But it's definitely simpler if you can use a flow tracer. Otherwise, you got to deal with the realities of the molecule you want to study. So people can do OH easily because it's been done. They can do NO, CH, CH2O. Flame people do this. But the flow tracers makes it a lot simpler if you're trying to measure temperature and mixing. There's more to be done on these species. I've got some new ideas on species we're going to study. These are, okay. That says CO2. I think probably, those are naturally present, but it's not so clear how you do CO2, unless you do IR PLIF. There's a lot of interest right now in high-speed PLIF and multi-parameter imaging. The holy grail would be if you could combine this with velocimetry. That's the holy grail. So this is my last slide. I think I was forced into start working with lasers when they hadn't been around very long. Lasers keep getting better and better. Cameras get better and better. There's no shortage of opportunities in this field. I think we'll see eventually this just becomes increasingly routine. I think people will be as good at this as they are probably at coding thermocouples for flames. This should have been packaged. The availability of packaged systems will grow. Certainly the tunable diode laser stuff is going to get more and more common. High repetition rate will become more common. I'm working on new tracers. I'd like to find some better tracers. I think we'll continue to see this in combustion. And energy sciences generally, laser diagnostics will just become more and more common. So here's my little saying. I think the future for laser diagnostics is bright. Sorry for the joke. Thank you for attending my short course. Best wishes to you for your future. I'm happy to take any last questions. Questions? So my notes, you can go back and study the notes. Sometimes I know I go a little too fast, but the idea is I want you to see a lot of stuff. You can study that which you wish. If you wish, you don't have to. But, and there's some good books, and I've referenced some books. Yes?
Would one of the reasons why you would choose acetone over toluene or vice versa be the temperature range that you're looking at, or also the mixture that you're using?
Different reason. Why would you use acetone over toluene? Toluene is more temperature sensitive and highly sensitive to oxygen. Acetone is not so sensitive to oxygen. So if you've got to do this in air, you have to use acetone or a ketone. On the other hand, if you want to measure the fuel-air ratio, now you can use toluene because it's inversely proportional. So problems are oftentimes opportunities. So it's toluene strongly impacted by oxygen. So in many regimes, it's almost like the signal's proportional to toluene over oxygen. So if you trace the fuel with toluene, this is a way to measure fuel-air ratio. But why would you use one over the other? I would say you use the ketones when you want to minimize the influence of oxygen, and you use the toluene when you want it, or when you want the higher. Toluene is more temperature sensitive. And you could do one laser, 2 cameras. I think that's kind of an easier, cheaper strategy. But I believe there's some better tracers that we're going to work on. Right now, people use acetone, 3-pentanone, 2-pentanone. The engine people want to pick ones that have properties similar to gasoline. They want ones that have similar vapor pressures. So that's how they pick them. If we have a flow field and we can keep oxygen out, we can use toluene and get all the sensitivity of toluene. Yes?
So when you're looking for new tracers, do you go back to those initial things you were teaching us about, like which lines, and basically look at properties like that? So
where would you go for new tracers? Well, all of these tracers that I'm telling you about now, today, or in the last hour, are big molecules. So it suppresses the details of the spectroscopy, but it brings in what I call photophysics. So if it's an isothermal isobaric, life is easy. If it's a compressible flow, now I got to be a little careful, but I need knowledge of the photophysics, and I need some kind of a model. We work on that. The small molecules means you have to understand the spectroscopy, pay attention to line shapes. But if you're trying to measure species which are formed in the flow, like NO or OH or formaldehyde or CH, that's what you have to do. So, but the tracer-based schemes, if you're more of a fluid mechanics person, obviously the way to go. It's just so much simpler. You know, my fluid student, laser with no knobs, he just had to form an intersheet. Camera, no knobs. He's doing fluid mechanics in a day. So a lot hinges on what you're trying to do. If you're trying to study plasma-enhanced combustion, you got to pick species that are there. Temperature range is important. Maybe you want to do imaging at 10,000 Kelvin. Well, you got to pick something that absorbs and fluoresces at 10,000 Kelvin. Probably an atom. It's probably an atom. So you have to kind of pick. But the concepts of absorption and fluorescence are there. You've now seen it for big molecules and small molecules, and atoms are similar. So you have to kind of decide on the problem. There's no one answer. There's no one approach. Well, Beer's law of absorption is an approach, but you have to decide what species you're going to do and what your limits are. But, anything else? Yes.
What's the
what's your measurement resolution in terms of temperature? Can you look inside of a shock?
Can you look inside of a
Shock.
shock? Okay. What's the measurement resolution of a sensor? Can you look inside of a shock? Shock waves are usually a few mean free paths thick. So if you want to look, you've got to go to low pressure to spread the shock wave out. You can do that. So you can spread it out so that it's a millimeter thick. You can spread it out so that it's as thick as a flame. And can you look inside? Yes. Now that's an interesting question. You look inside a shock wave, what's the temperature?
It's hard to know.
It's hard. It may not even be defined. You go from one temperature to another temperature over a distance of 5 mean free paths. What's the temperature in between? Really, you have to deal with the velocity distribution function of the atoms and molecules. This is a very subtle question. So I worked on this. In fact, I was telling somebody about this. I was interested in looking at the evolution of the population density in specific rotational quantum states through a shock wave. I knew how to do this. You could measure, you set your laser so you populate, so that you measure the population in j equals 0, and then 1, and then 2, and study that structure. I thought that would be very interesting. But I never finished it. But you could do that. But translational temperature, even when there's a translational temperature, there may not be a rotational temperature. So you're measuring, so the power of this is you're measuring populations in quantum states. That's a good thing. Especially if there's no temperature. But if there's a temperature, so anyway, could you do it in a shock wave? Yes, only if you spread it out. People do this in flames. Flames are thin. But you have to focus down to a narrow region. Yes?
Could you elaborate a little bit on the seeding technology?
On the what?
Seeding technology.
Seeding technology. Could you elaborate on the seeding technology? So you're talking about the tracer now, or? Yeah. So we're not seeding particles. We're seeding gases. So it needs to be a gas. Usually sometimes they're liquids. It has to have a vapor pressure you can deal with. So we bubble acetone through some, we bubble nitrogen, say, through an acetone, and we control the temperature, which gives us the vapor pressure. So we have to generate the vapor and carry it to the experiment. So if you start with one that has a high vapor pressure, it's a lot easier than if you don't. But some of the most interesting tracers that I'm interested in right now have very low vapor pressure. So that's a challenge. But they have very desirable photophysics properties. So it could be that there's a trade-off that you have to work harder to get maybe you have to heat it hard. You have to heat it harder to get the vapor, but it could be very nice vapor. If you're just seeding NO or something like that, it's of course simple. Go ahead, one more.
What about metal species?
Metal species. What about metal species? Well, you could probably seed, you can seed things, you could seed molecules that are comprised of 2 atoms that may come apart and give you one that you're after, something like that. Or you could possibly embed some metal. If you wanted metal, you could probably have a liquid which, when it evaporated, would give you something that you want. Yeah, but now you're getting specific. So seeding then becomes a problem. And of course, maybe what you're trying to study is the evaporation rate of some droplet that's got this. There's problems or opportunities. Yes.
Could you maybe comment on difficulties in doing this in a spray system? You mentioned
Yes.
that kind of in the beginning.
Yeah. So difficulties of doing polyphony spray. So the first thing is, you saw from the picture that I had, light comes in, it bounces off the droplets, and it's all over the place at the color of the laser. So made for a pretty picture, but it's bad news for my detector. So, but the laser, so you can't, the way you always get rid of interference emission or scattered light is always spatial strategies, spectral strategies, and temporal gating. So those are the elements that you have available to you to beat away what you don't want. So, but droplets are bad because they're bouncing light into your detector. So you have to worry about it. It's harder. Similarly, if you were studying, say, a sooting flame, same problem. You're going to get light from the soot, black body light from the soot. You're going to get scattered light from the soot. So the first thing is you got to get light through to the place you want to interrogate. And then you have to understand it. So there's different problems. One is that you may be attenuating the light beam so that you may not know how much intensity you have to produce the fluorescence. Remember, a signal is proportional to how many photons are coming into a measurement volume. So it just gets harder. Things get harder at high pressure or when they're multi-phase. That can be done, but now other people would say, actually, I want to image the droplets, and I want you can get a signal from the droplets, scattered light signal, but you can also get fluorescence from the liquid. So some people want to study that. In fact, some of the best work in imaging is in liquid flows. Pure liquid flow, not droplets, but pure liquid flows. You get some great signals. So there's no simple answer except when you get into multi-phase flows, things get harder. Because fluorescence is a weak process. And your detector is sitting there and it's looking at some wavelength of light. And you might narrow it down with a filter, but it can't discriminate. If photons come through, you get a signal. You may not want that. So that's the trouble with fluorescence. The quenching problem and the fact that the signals in a container where there's a lot of scattered light, Raman people have an even bigger problem. People who do Raman spec, it's such a weak process. You have to work really hard. Rayleigh people, you have to work so hard to get rid of the competition. So multi-phase flows are harder, for sure.